Hello friends, welcome to my lecture on Fourier series. Fourier series was introduced by the French physicist Joseph Fourier in 1807 while he was investigating the conduction of heat along a wire. Now it is very useful in the study of heat conduction, mechanics, concentrations of chemicals and pollutants, electrostatics and acoustics, etc. Fourier series is an infinite series representation of a periodic function in terms of the trigonometric sine and cosine functions. It is a very powerful method to solve ordinary and partial differential equations, particularly with periodic functions appearing as non-homogeneous terms. While Taylor's series expansion we know is valid only for functions which are continuous and differentiable, Fourier series is possible not only for continuous functions, but for periodic functions, functions which are discontinuous in their values and derivatives. Further, because of the periodic nature, Fourier series constructed for one period is valid for all values of x. Let us see how we define a periodic function. A function f(x) is said to be periodic if f(x) plus t is equal to f(x) for all real x and for some positive real number t. T is then called the period of f(x). Now if a function f(x) has a smallest period t greater than 0, then it is called the positive period of f(x). For example, the primitive period of sin x and sin 2x are 2 pi and pi respectively. Examples of periodic functions without primitive period are f(x) equal to constant. If you take f(x) equal to constant, then any t greater than 0 is a period of f. Okay. Then you take any t greater than 0 is a period of f(x), because f(x) plus t is equal to constant. Okay. When you take any t greater than 0, x plus t is also a real number. So, f(x) plus t by definition is a constant, and which is the constant which is equal to f(x), and this is valid for all x belonging to R. So, if the function f(x) is a constant function, it can be regarded as a periodic function with any period t greater than 0. And so, if you take t to be any number greater than 0, then we do not have any smallest value of t greater than 0. So, if f(x) is constant, then it does not have a primitive period. Now, if you take f(x) equal to 0 when x is rational and f(x) equal to 1 otherwise, in this case you can see you can take any positive real rational number t. Okay. Let t greater than 0 be a rational number. Then if x is rational, because t is rational, so x plus t will be rational, and so f(x) plus t will be equal to 0. Okay. And when x is irrational and t we have assumed to be rational, then x plus t will be rational. Okay. And f(x) plus t is equal to 1 if x is irrational. Here we are assuming x to be rational. Okay. So, f(x) plus t is equal to f(x) if x is rational and f(x) plus t is equal to f(x) if x is irrational. Okay. Now, we know that the set of positive rational numbers does not have any smallest positive value. Okay. So, there does not exist a smallest positive rational number. So, we can say that the example of f(x) equal to 0 when x is rational and f(x) equal to 1 otherwise does not have a primitive period. Every positive rational number is a period of this function, and the set of positive rational numbers does not have a smallest positive rational number. So, f(x) does not have a primitive period. Now, let us consider the Fourier series. Let f be a periodic function of period 2 pi, which can be represented by a trigonometric series. This is the trigonometric series f x equal to a naught by 2 plus sigma n equal to 1 to infinity a n cos n x plus b n sin n x. You can see that it is made up of trigonometric functions cos n x and sin n x, which are 2 pi periodic. Such a series is called a trigonometric series. Now, if term by term integration of this series is allowed, then we obtain the so called Euler formula. You can integrate this on both sides of this equation with respect to x over the interval minus pi to pi, then integral over minus pi to pi f x dx will be equal to a naught by 2 integral over minus pi to pi dx plus sigma n equal to 1 to infinity a n integral over minus pi to pi cos n x dx plus b n integral over minus pi to pi sin n x dx. Okay. Now, integral over minus pi to pi dx will be equal to 2 pi, okay, while integral over minus pi to pi cos n x dx is 0 and integral over minus pi to pi sin n x is also 0. Integral over minus pi to pi sin n x dx is 0 because sin n x is an odd function of x, and integral over minus pi to pi f x dx is 0 if f x is an odd function. So, integral over minus pi to pi sin n x dx is 0, integral over minus pi to pi cos n x dx is 0 because integral of cos n x is sin n x over n and its value at pi and minus pi is 0. So, this is 0 and therefore, what do we have? Minus integral over minus pi to pi f x dx equal to a naught by 2 into 2 pi. So, that means a naught pi, okay, or we can say a naught equal to 1 over pi integral over minus pi to pi f x dx. Okay. Now, if we want to derive the formula for a k, then you multiply both sides by say cos m x, okay, integrate with respect to x over the interval minus pi to pi. So, what we will have? Integral over minus pi to pi, we are multiplying by cos m x. So, f x cos m x dx equal to a naught by 2 into integral over minus pi to pi cos m x dx plus sigma n equal to 1 to infinity a n integral over minus pi to pi cos m x cos n x dx plus b n integral over minus pi to pi cos m x sin n x dx. Okay. Now, integral over minus pi to pi cos m x dx is 0 because integral of cos m x is sin m x over m, its value at pi and minus pi is 0. So, this integral is 0, integral over minus pi to pi cos m x cos n x dx is also 0. Actually, we know that 1 cos x sin x cos 2x sin 2x cos 3x sin 3x and so on. They satisfy orthogonal property that they are orthogonal functions. Okay. So, that means that if you take any function f here and a function g there, then integral then the inner product of f with g, okay, is equal to integral over minus pi to pi f x into g x dx. This is equal to 0. Okay. So, these functions 1 cos x sin x cos 2x sin 2x cos 3x sin 3x and so on, okay, cos n x sin n x, they satisfy orthogonal property. That means, if you take any two functions f and g from this set, okay, where f is not equal to g, f and g are distinct functions, then integral over minus pi to pi f x dx is 0. So, because of this property, okay, we have integral over minus pi to pi cos m x cos n x dx is 0 when m is not equal to n, and integral over minus pi to pi cos m x into sin n x dx is 0. Now, what will happen when m is equal to n? So, when m is equal to n, what will happen is that we will have integral over minus pi to pi. So, we multiply by cos m x, and therefore, integral over minus pi to pi f x cos m x dx is equal to a m, because when n is not equal to m, okay, integral of cos m x into cos n x dx is 0 over the interval minus pi to pi. So, when n is equal to m, we have minus pi to pi cos square m x dx, okay, and this can be written as a m integral over minus pi to pi 1 plus cos 2 m x by 2 dx. We can integrate this expression and we get x plus sin 2 m x by 2 m by 2. Okay, so, this is equal to a m into pi, because sin 2 m x is 0 when x is pi or minus pi. So, this implies that a m equal to 1 over pi integral over minus pi to pi f x cos m x dx. Now, here m is any positive arbitrary positive integer, So, we get the value of a k for all k. So, we get a k equal to 1 by pi integral over minus pi to pi f x cos k x dx, where k takes value 1, 2, 3 and so on. Okay. Now, in order to find this b k, we multiply this equation by sin m x, okay, and then integrate over minus pi to pi. So, just like we have found the value of a k's, we multiply f x by sin m x, integrate over minus pi to pi, then what will happen? Integral over minus pi to pi sin m x dx will be 0 here, and here we will have integral over minus pi to pi sin m x into cos n x dx, that will also be 0. Integral over minus pi to pi sin m x into sin n x dx will be 0 when n will be not equal to m, okay, and when n is equal to m, we will have integral over minus pi to pi sin square m x dx. Integral over minus pi to pi sin square m x dx is also pi, okay. So, we will get bm into pi equal to integral over minus pi to pi f x into sin m x dx, and therefore, we will get the value of bm as 1 over pi integral over minus pi to pi f x sin m x dx, but m is arbitrary positive integer. So, we get the value of b k for all k, b k equal to 1 over pi integral over minus pi to pi sin x sin f x into sin k x dx. K takes values from 1, 2, 3 and so on. Now, the value of a naught and the value of a k, okay, the value of a naught can be merged with the value of a k, because the value of a naught can be retrieved from the expression for a k. If you put k equal to 0 in the expression for a k, you get a naught as 1 by pi integral over minus pi to pi f x dx. Okay. So, we get the value of a naught from the expression for a k, therefore, a naught is merged with the value of a k, and k varies in a k varies from 0, 1, 2 and so on. Okay. Now, let us see that because of the periodicity of the integrand, here you can see f x is 2 pi periodic, okay, cos k x is 2 pi periodic and sin k x is 2 pi periodic. So, f x into cos k x is 2 pi periodic, here f x into sin k x is 2 pi periodic. Therefore, integral over minus pi to pi can be replaced by any integral where the length of the interval is 2 pi. Okay. So, integral over minus pi to pi can be replaced by integral over a to a plus 2 pi, where a is any real number. In particular, integral over minus pi to pi we can replace by integral over 0 to 2 pi. So, because of the periodicity of the integrand, the interval of integration can be replaced by any other interval of length 2 pi, for instance by the interval 0 less than or equal to x less than or equal to 2 pi. Now, if f is continuous or merely piecewise continuous, piecewise continuity means it is continuous except for finitely many finite jumps in the interval of integration. The integrals in 2 which we call as Euler formulas, okay, these integrals exist even when the function f x is having only finitely many jumps in the interval of integration. Okay. So, finitely many finite jumps in the interval of integration, then also these integrals exist, and so we may compute the value of a k for k equal to 0, 1, 2 and so on, and v k for k equal to 1, 2, 3 and so on, and form the trigonometric series a naught by 2 plus a 1 cos x plus b 1 sin x and so on, a n cos n x plus b n sin n x and so on. Now, this series is then called the Fourier series of f, okay, and its coefficients a k and b k, are called the Fourier coefficients of f x. Now, let us talk about the convergence of this Fourier series. When will it represent the function f x? Okay. So, there are sufficient conditions for that. The sufficient conditions are the following. This theorem gives us the sufficient conditions for the representation of a function by a Fourier series. If a periodic function f x with period 2 pi is piecewise continuous in the interval minus pi to pi and has a left hand and right hand derivative at each point of that interval, then the corresponding Fourier series 3 with coefficients 2, this Fourier series, okay, this Fourier series with coefficients given by these equations 2, okay, is convergent. Its sum is f x except at a point x naught where the function is except at a point x naught at which the function is discontinuous, and the sum of the series then is the average of left hand and right hand limits. Okay. So, the sum of the series will be equal to f x at each point of continuity of f, and the sum of the series will be the average of left hand and right hand limits at each point of discontinuity of f. If the function f is piecewise continuous in the interval minus pi to pi and has left hand and right hand derivative at each point of the interval minus pi to pi. Now, let us consider this example f x equal to 0 when minus pi is less than x less than 0, and f x equal to pi minus x when 0 less than or equal to x less than pi. Let us draw the graph of this function over the interval minus pi to 0. This function is 0, so we have this graph, okay, and when x is equal to 0 the value of the function is pi. So, here we put a circle, this is let us say pi, okay. So, here x at x equal to 0 the value of the function is pi, and when x is going to pi f x goes to 0. So, the graph of the function is like this, okay. Now, this function is defined over the interval minus pi to pi, okay. You can see that f x is defined over the interval minus pi to pi. Over the interval minus pi to pi, the point x equal to 0, okay, is the point of discontinuity of f, okay. F x is discontinuous at x equal to 0. You can see this from the graph, because over the interval minus pi to 0 f x is 0, and then over the interval 0 to pi it is given by pi minus x. So, left hand limit at 0 is 0, while the right hand limit at 0 is pi, okay. So, left hand and right hand limits are not equal, and therefore, the function is not continuous at x equal to 0. Everywhere else on the interval minus pi to pi f x is continuous, okay. Now, we can find the value of a naught. Now, you can see that the value of a naught here is given by 1 over pi integral over minus pi to pi f x dx. So, this integral will reduce to the integral over 0 to pi f x dx, because over the interval minus pi to 0 f x is 0. So, 1 over pi integral over 0 to pi f(x) is pi minus x. So, we put pi minus x here for f(x), and this will give you 1 over pi pi x minus x square by 2. So, let us put the values, the limits, then we have 1 over pi, and this will be pi square minus pi square by 2. So, we get 1 over pi into pi square by 2, that means pi by 2. Okay. So, this value a naught is equal to pi by 2. We can similarly find the value of a n. A n is given by 1 over pi integral over minus pi to pi f(x) cos n x dx. Again let us use the fact that f(x) is 0 over the interval 0 to minus pi to 0. So, we have 1 over pi integral over 0 to pi, and over 0 to pi f(x) is given by pi minus x. So, pi minus x cos n x dx. Let us integrate this by parts. Okay. Then we have pi minus x into sin n x by n then 0 to pi, derivative of pi minus x is minus 1 into sin n x by n. So, this is 1 over pi. Okay. When x takes the value pi, pi minus x is 0. Okay. Even sin n pi is 0, and when x is equal to 0, this is pi minus x is pi, but sin n 0 is 0. So, we get 0 here, minus minus plus, and then we have integral of sin n x over n. So, sin n x, the integral of sin n x is minus cos n x over n. So, that means minus cos n x over n square we have. Okay. So, this will be equal to 1 over pi into n square, and we put the limits, we get minus cos n pi plus 1. So, 1 minus cos n pi, which will be equal to 1 minus minus 1 to the power n divided by pi into n square. We can also find Bn, Bn equal to 1 over pi minus pi to pi f(x) sin n x dx. So, this integral will also reduce to 1 over pi integral over 0 to pi f(x) is pi minus x sin n x dx. Okay. So, this will be equal to, again we integrate by parts, 1 over pi. So, pi minus x into minus cos n x by n 0 to pi, then we have 0 to pi, derivative of pi minus x is minus 1 into minus cos n x by n dx. Okay. So, this is 1 over pi. When we put x equal to pi, pi minus pi is 0. So, we get the value 0, but when we put the lower limit, pi minus x becomes pi, and here what we get, minus cos n pi over n, minus cos n pi over n, and together with the negative sign. So, we get cos n pi by no, we have when we put the first upper limit gives 0, right, then minus, we put the lower limit. So, pi minus 0 means pi, and then minus x equal to 0. So, pi minus 0 is pi, and this is minus 1 over n. Okay. Yeah, and this is minus 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 integral of cos n x is sin n x by n. So, we get sin n x by n square 0 to pi. Okay. So, this is 0, sin n x is 0 at x equal to 0 as well as x equal to pi. So, we get 1 over pi into pi by n, that is we get the value n. So, a n is 1 by n, b n is 1 minus 1 to the power n over pi n square. So, we get the value of a n, we get the value of b n. We put these values in the Fourier series for the function f, and Fourier series will have the sum f x over the points at the points where the function is continuous. Function is continuous in the open interval minus pi to 0 and over the interval 0 to pi. Okay. So, f(x) equal to a naught by 2, a naught by 2 means pi by 4, and then sigma n equal to 1 to infinity a n cos n x plus b n sin n x. So, this is the Fourier series of the function f in the open interval minus pi to 0 and 0 to pi. Now, at the point x equal to 0, the right hand side of the Fourier series becomes the Fourier series at x equal to 0, the Fourier series becomes put x equal to 0 in this. So, pi by 4 plus sigma n equal to 1 to infinity 1 minus 1 to the power n divided by n into n square pi cos 0 is 1 and sin 0 is 0. Okay. So, we have pi by 4 plus sigma n equal to 1 to infinity 1 minus 1 to the power n over n square pi equal to average of left hand right hand limits. So, f 0 minus plus f 0 plus divided by 2. Okay. Now, f 0 minus is 0, f 0 plus is pi. So, this is pi by 2. Okay. So, what we can say now? We can say that we have pi by 2 equal to pi by 4 plus sigma n equal to 1 to infinity 1 minus 1 to the power n divided by pi into n square. Okay. Pi into n square cos n x. Okay. So, pi by 2 minus pi by 4 is pi by 4, and so we get pi by 4 equal to 1 over pi sigma n equal to 1 to infinity 1 minus 1 to the power n divided by n square, okay, cos n x. Cos n x is 1, okay, at x equal to 0. So, we have to put that also. So, this is actually 1, cos n x is, we replace this by 1. Okay. So, we have actually this, because at x equal to 0 cos n x is 1. So, we have pi square by 4 is equal to sigma n equal to 1 to infinity 1 minus 1 to the power n by n square. Now, let us notice when n is an even integer, okay, then 1 minus 1 will be 0, because minus 1 to the power n will be 1. Okay. So, this is 0, this expression is 0 when n is even, and it is 2 by n square when n is odd. Okay. So, this is equal to sigma n equal to 1 to infinity when n is odd. We are considering only odd integral values of n over the set of numbers 1, 2, 3 and so on up to infinity. So, this we have 2 by n square, okay, and this we can also write as replacing n by 2 n minus 1, we have n equal to 1 to infinity 2 by 2 n minus 1 whole square. Okay. So, what we get? We get that sigma n equal to 1 to infinity 1 by 2 n minus 1 whole square is pi square by 8. Okay. Thus, we have sigma n equal to 1 to infinity 1 over 2 n minus 1 whole square equal to pi square by 8. So, we get the sum of the series 1 plus 1 by 3, or you can say 1 upon 1 square plus 1 upon 3 square. So, 1 by 1 square plus 1 by 3 square, 1 by 5 square and so on. This is equal to pi square by 8. So, by Fourier series we can also determine the sum of many infinite series which are otherwise not easy to find. Okay. So, let us now go to next slide. So, this is how we determine the Fourier series for the given function, and we have also seen that we can determine the sum of the infinite series 1 plus 1 by 3 square plus 1 by 5 square plus 1 by 7 square and so on as pi square by 8. Okay, now let us consider now we will consider Fourier series of functions having arbitrary period. In applications, periodic functions rarely have period 2 pi. Therefore, in order to find the Fourier series of a periodic function f t with period, let us say t, f t is not having period 2 pi, okay, it is having an arbitrary period t, then we use the change of scale. Okay. So, we will use the change of scale. We introduce a new variable x such that f t as a function of x has period 2 pi. Let us define t equal to t over 2 pi into x. Then when x will be pi, t will be minus t by 2, and when x will be minus pi, t will be minus t by 2, and when x will be plus pi, t will be pi by 2. So, x equal to plus minus t will correspond to t equal to plus minus t by 2, and f t, the function f t will change to f of t over 2 pi x, which we can write as some function phi x. Okay. Now, this function phi x is a 2 pi periodic function. You can see, because phi of x plus 2 pi is equal to by definition phi of x plus 2 pi is f of t over 2 pi into x plus 2 pi, which is f of t x over 2 pi plus t. Okay. We are assuming that f is periodic with period t. So, f of t x over 2 pi plus t will be f of t x over 2 pi. Okay. F of t x over 2 pi is phi x. Okay. So, phi is now 2 pi periodic, and therefore, we can write the Fourier series for the function phi. Okay. We can determine Fourier coefficients. Fourier coefficients are given by a k equal to 1 over pi minus pi to pi integral over minus pi to pi phi x cos k x dx, where k takes values 0, 1, 2, 3 and so on, and b k is given by 1 over pi integral over minus pi to pi phi x sin k x dx, k takes values 1, 2, 3 and so on. Okay. So, we can get the expressions of a k and b k in terms of the function phi. Now, let us put the value of phi x. Okay. So, phi x is f of t x over 2 pi. So, let us put that value. So, a k equal to 1 over pi integral over minus pi to pi f of t x over 2 pi x cos k x dx. Okay. K is 0, 1, 2, 3 and so on, and b k will become 1 over pi integral over minus pi to pi f of t x over 2 pi sin k x dx, and k takes values 1, 2, 3 and so on. Now, we have assumed that x is equal to 2 pi t over t. Okay. From here we can see x is equal to 2 pi t over t. Okay. So, x is 2 pi t over t, and therefore, dx equal to 2 pi over t into dt. Let us make that substitution. So, when we will change x to t, okay, f of t x over 2 pi will change to f t function. Okay. So, this f of t x over 2 pi will become f t, and here we will have in the expression for a k we will have cos of 2 pi k t by t, because x is 2 pi t by t. So, cos 2 pi k t by t dx will be 2 pi over t dt. Okay. So, we will have a k equal to 1 over pi, the limits of integration will become minus pi will go to minus t by 2, pi will go to t by 2, and we will have here f t, this will become f t, and cos 2 pi k t divided by t dx will be 2 pi over t dt. Okay. So, this pi will cancel with this pi, 2 over t is a constant, we can write it outside. So, 2 over t minus t by 2 to t by 2 f t cos 2 pi k t by t dt. Okay. So, we get this value of a k. Similarly, we can write v k equal to 2 over t integral over minus t by 2 to t by 2 to t by 2 f t sin 2 pi k t by t dt. Okay. So, that is the value of b k, and the Fourier series will become a naught by 2 sigma n equal to 1 to infinity a n cos n x. N x is 2 pi t by t. So, cos 2 pi nt by t, bn sin nx. So, nx will be replaced by 2 pi nt by t. So, we will have bn sin 2 pi nt by t. So, this is the Fourier series for the function f if it is of period t. The interval of integration may be replaced here because f is t periodic, okay, and sin 2 pi k t by t is also t periodic. So, we can replace the interval of integration minus t by 2 to t by 2 by 0 to t. Okay. Now, let us say for example, f t equal to t over the interval minus 2 to t 2. So, this is your minus 1, let us say this is minus 2. So, we have this by equal to x function over the interval minus 2 to 2. Okay. So, f t equal to t. Okay. So, this is t, this is f t. Now, and we are given that f is periodic with period 4. Okay. So, the graph of f over the interval minus 2 to 2 is then repeated over the other intervals of length 4, say that is from 2 to 6 or from minus 6 to minus 2. Okay. So, we can just repeat this graph. Okay. Now, since you can see here that f minus t, okay, if you put f of in place of t you put minus t, then f of minus t is minus t. Okay. So, I can write it as minus of f t. Okay. This is valid for all t belonging to minus 2 2. Okay, because of the definition of f t. So, this means that f is an odd function of t. Okay. So, integral of, so the value of a naught is equal to we can find the value of a naught from here 2 over t minus t by 2 to t by 2 f t and k is 0. So, f t dt. Okay. So, we have 2 by t integral over minus t by 2 to t by 2 f t dt. Okay. T is equal to 4 here. So, 2 by 4 integral minus 2 to 2 f t dt. Now, f is an odd function. Okay. So, integral over minus 2 to 2 f t dt is equal to 0. Now, similarly, if you find a k, okay, a k equal to 2 over t integral over minus t by 2 to t by 2 f t cos 2 pi k t by t dt, then it will become 2 by 4 integral over minus 2 to 2 f t t is 4. Okay. So, 2 pi k t by 4 means pi k t by 2 dt. Okay. Now, f t is an odd function, cos pi k t by 2 is an even function, product of an even and odd function is an odd function. So, the integrand is an odd function and therefore, its integral over minus 2 to 2 is 0. Okay. For all k equal to 1, 2, 3 and so on. Okay. So, a naught is 0, a k is 0 for all k 1, 2, 3 and so on. So, we just have to calculate b k's. Okay. So, b k is given by b k is equal to 2 over t integral minus t by 2 to t by 2 f t sin 2 pi k t by t dt. Okay. T is 4. So, we have 2 by 4 that is 1 by 2. Okay. And then minus 2 to 2 f t is into sin pi k t by 2 dt. Now, f t is an odd function of t, sin pi k t by 2 is also odd function of t, therefore, product of odd function with odd function is an even function. So, we have integral over minus 2 to 2 we can replace by 2 times integral over 0 to 2. So, 2 times 2 by 2 integral over 0 to 2 f t is t. Okay. Sin pi k t by 2 dt we get. Okay. So, we get the value of we can integrate this by parts, okay, and evaluate the value of b k. The value of b k comes out to be 4 times minus 1 to the power n plus 1 over n pi, and we then have the Fourier sine series, because the cosine terms vanish and also the cos term vanishes. Okay. So, f t is equal to sigma n equal to 1 to infinity b n sine 2 pi n t by t, t is 4. So, pi n t by 2. Okay. So, sin pi n t by 2 here we have, and then we put the value of b n, that is 4 over pi minus 1 to the power n plus 1 over n. Okay, now let us see the Fourier series of an even function f t of period t is a Fourier cosine series. As I said just now, if f is an even function, okay, if f is an even function, then we will have a k equal to 2 over t integral over minus t by 2 to t by 2 f t cos 2 pi k t by t dt. Okay. F is an even function, cosine function is also even, so their product is even. So, we get 2 integral over minus t by 2 to t by 2 becomes 2 times integral over 0 to t by 2. So, we get 4 over t integral over 0 to t by 2 f t cos 2 pi k t by t dt, while b k, this will be true for all k equal to 0, 1, 2 and so on. Okay. And b k will be 2 over t integral over minus t by 2 to t by 2 f t sin 2 pi k t by t dt. Okay. F is an even function, sin 2 pi k t by t is an odd function. So, integral over minus t by 2 to t by 2 is 0, this is 0 for all k. Okay. And so, the Fourier series will reduce to a naught by 2 plus sigma k equal to 1 to infinity a k cos 2 pi k t by t. Okay. That is this. Okay. So, where the value of a k, okay, will be given by this integral. This integral can be written as 4 by t integral over 0 to t by 2 f t cos 2 pi k t by t dt. Now, if we have f is an odd function, okay, f is an odd function, then just now we have seen the example of f t equal to t. In the case of an odd function, the a k is 0 for all values of k equal to 0, 1, 2, 3 and so on up to infinity, and b k becomes 4 by t, b k becomes 4 by t, because the integrand will become even in the case of b k. So, 0 to t by 2 f t sin 2 pi k t by t dt. Okay. And this is the value of b k for k equal to 1, 2, 3 and so on. Okay. And the Fourier series will become sigma k equal to 1 to infinity b k sin 2 pi k t by t. Okay. So, this is the situation. Now, if we have two functions f 1 and f 2, okay, then the Fourier coefficients of a sum f 1 plus f 2 are the sums of the Fourier coefficients of f 1 and f 2. This is very easy to see. You can see that if we have some function f 1 plus f 2, then it for this some function f 1 plus f 2, a k will be equal to 2 over t integral over minus t by 2 to t by 2 f 1 plus f 2 cos 2 pi k t by t dt. Okay. And we can, this is valid for k equal to 0, 1, 2 and so on. Okay. And this I can write as 2 over t integral over minus t by 2 to t by 2 f 1 t cos 2 pi k t by t dt plus 2 over t integral over minus t by 2 to t by 2 f 2 t cos 2 pi k t by t dt. So, for the Fourier series of the function f 1 plus f 2, we see that a k, which is the coefficient of cos 2 pi k t by t, is the sum of the Fourier coefficients of f 1 and f 2, which are the Fourier coefficients of the cos 2 pi k t terms, cos 2 pi k t by t terms in the case of functions f 1 and f 2. This is, let us say f 1 plus f 2 we write as its Fourier series as a naught by 2 plus sigma k equal to 1 to infinity a k cos 2 pi k t by t plus b k sin 2 pi k t by t. Okay. This is the Fourier series for the function f1 plus f2. Then this is the Fourier coefficient ak1 ak for f1 function, okay, and that this one is ak for the f2 function. This ak is for f1 plus f2 function, okay, this one. Okay. So, Fourier coefficient of ak for f1 plus f2 is sum of the Fourier coefficients of f1 and f2, the corresponding Fourier coefficients of f1 and f2. Similarly, vk you can see vk for the function f1 plus f2 is sum of bk for f1 plus bk for f2. So, Fourier series for the function f1 plus f2 can be found by the Fourier series for the function f1 and the Fourier series for the function f2. We can separately find and take their we can separately find the Fourier coefficients for f1 and f2 and then add them to get the Fourier coefficients for f1 plus f2. Now, let us consider two half range expansions. In various physical and engineering problems, we need to find the Fourier series of a function f t which is defined on some finite interval, say 0 less than or equal to t less than or equal to L. So, it is defined over the interval 0 to L, over this interval. Okay. As it is immaterial, whatever be the function outside the range 0 less than or equal to t less than or equal to L. So, we extend the function to cover the range minus L to L. So, we define the function on our from our side on the other half of the interval, that is minus L to 0. Okay. So, now the function will be defined over the interval minus L to L. Now, we define the function over the interval minus L to L either as an even function or as an odd function. Okay. So, the new function will be either odd or it will be even function. The Fourier expansion of such a function of half the period therefore consists of sine or cosine terms only. Half the period means we know the function only over the half period 0 to L. Okay. We are defining over the other half period minus L to 0 by either an odd extension or by an even extension. Okay. So, the resulting function f1 you can call the resulting function new function f1 is either even or it is an odd function. Okay. So, let f1 t denote odd periodic extension of f. Okay. Then now t is equal to 2L. Okay. The function is defined over the interval minus L to L. So, since t is equal to 2L, the Fourier series of f1 t, now we are defining f1 as an odd periodic odd function, therefore, its Fourier series will consist of only sine terms. Okay. So, its Fourier series will be sigma n equal to 1 to infinity b n sine 2 pi n t over t. Now, t is equal to 2L. Okay. T is equal to 2L. So, let us put the value here, we get sigma n equal to 1 to infinity b n sine pi n t over L. The b n's are given by 2 over t integral over minus t by 2 to t by 2 f1 t sin 2 pi n t by t dt. Let us put t equal to 2L here. Okay. So, we get integral over minus L to L. This is 2 over L integral over minus L to L f1 t sin pi n t by L dt. Okay. Now, f1 t is an odd function, sin pi n t by L is also an odd function. So, we can write it as this is 1 over L, this is 2 over 2L means 1 over L. Okay. So, using the fact that f1 t into sin pi n t by L is an even function, we can write 2 over L 0 to L, f1 t now becomes f t because over the interval 0 L f1 t coincides with f t sin pi n t by L dt. So, this is how if we know the function over the interval 0 to L by defining over the other half, that is minus L to 0, by the odd periodic extension we can find the Fourier sine series for the function f. whose Fourier coefficient Bn is given by 2 over L 0 to L f t sin pi n t over L dt. You can see here that the function's values over 0 to L only are being used. Okay. In the case of an even periodic extension f1 t of f t, okay, f1 t will be an even function. So, we will have Fourier cosine series, okay. Ak will be given by then 2 over t integral over minus t by 2 to t by 2 f t cos 2 pi n t k t by t dt. Okay. So, this is 2 over 2 L, okay, t is 2 L and limits are minus L to L because t is 2 L. So, integral over minus L to L and f t cos pi k t by L dt. Okay. Now, f is even, cos pi k t by L is also even. So, I can write 2 over L 0 to L f t cos pi k t by L dt. Okay. And we have the Fourier cosine series. The Fourier cosine series will be a naught by 2 plus sigma k equal to 1 to infinity a k cos pi k t by L, where a naught and a k's are given by this integral, okay, k equal to 0, 1, 2 and so on. Okay. So, this is the formula. These are called half range sine and cosine series of the function f. Now, let us say for example, f t equal to t square, okay, f t equal to t square, it is defined over the interval 0 to t, 0 to 2. We want to find a Fourier cosine series and a Fourier sine series. If we want Fourier cosine series, we will extend the function f t over the other half interval minus 2 to 0 by taking a even periodic extension. So, we will define the function f t as an even function, okay, over the other half, okay, that is f t equal to t square when minus 2 less than t less than 0. Okay. So, if we define f t equal to t square, it will be an even function, okay, and then we will have its Fourier cosine series. So, a naught will be given by a naught will be given by 2 over L 0 to L f t cos pi k t by L dt. Okay. So, 2 over L 0 to L f t cos pi k t by L dt. Okay. L is equal to 2 here, okay. T is equal to 4, right, t equal to 4. So, and t is equal to 2L. So, L equal to 2. So, this is 2 over 2. So, that is 1. So, we get 0 to 2, okay. F t is t square cos pi k t divided by 2 dt. Okay. Be integrated by parts, substitute the limits, okay. When you want a naught, put k equal to 0. So, a naught will be equal to 0 to 2 t square dt, and what we get here, t cube by 3. So, 0 to 2. So, we get 8 by 3, okay. But here in the Fourier cosine series we have a naught by 2 here, okay. F t is equal to a naught by 2 plus sigma k equal to 1 to infinity a k cos pi k t divided by 2, okay. So, a naught by 2 will become then 4 by 3, we get this term, okay. And then we can get the value of a k for k equal to 1, 2, 3 and so on by integrating by parts the function t square cos k t by 2 and putting the limits. We will get this 16 over pi square minus 1 to the power n over n square, okay. So, this is the Fourier cosine series in this case. When we want Fourier sine series, we will define the function f t equal to t square over 0 to t, 0 less than t less than 2 and minus t square over minus 2 less than t less than 0, okay. Then f of minus t, okay. Suppose t belongs to 0 to 2 interval, okay. So, f of minus t will belong to then minus 2 to 0, okay, and therefore, we will get minus of minus t whole square, Okay. So, we will get here minus t square, okay, which is equal to minus f t. Okay. So, if we want odd periodic extension of the function f t, then we define f t equal to minus t square over the interval minus 2 to 0. Okay. Then a naught a k will be 0 for all k. Okay. We will get the value of b k. B k will be given by 2 over L 0 to L f t sin pi k t divided by L dt. Okay. L is equal to 2 and f t equal to t square. Okay. We can evaluate the integral and we get the value of b k for all k. The value of b k will be 8 over pi minus 1 to the power n plus 1 over k, 2 over k cube into pi square minus 1 to the power k over minus 1 by integrating by parts. So, that we can easily do. Now, let us come to the complex form of the Fourier series. The Fourier series of a periodic function f t of period t is given by f t equal to a naught by 2 plus sigma n equal to 1 to infinity a n cos 2 pi n t by t plus b n sin 2 pi n t by t. Let us use the Euler's formula for cos theta and sin theta. Cos theta is e to power I theta plus e to power minus I theta by 2, sin theta is e to power I theta minus e to power minus I theta by 2. Let us put these expressions for cos 2 pi n t by t and sin 2 pi n t by t. Okay. Then what we will get, cos, we will have cos theta. Okay. So, cos 2 pi n t by t, okay, will be equal to e to the power 2 pi I times 2 pi n t I by t plus e raised to the power minus 2 pi n t I by t divided by 2. Okay. And similarly for sin 2 pi n t by t, sin 2 pi n t by t will be equal to e raised to the power I 2 pi n t by t minus e raised to the power minus I 2 pi n t by t divided by 2 I. Okay. We put these values and then collect the coefficients of e to the power 2 pi n t I by t and e to the power minus 2 pi n t I by t. Okay. Then you will see that their coefficients are given by coefficient of e to power 2 pi n t I by t will be given by a n minus I b n by 2, okay, and the coefficient of e to the power minus 2 pi n t by t will be given by a n plus I b n by 2. If that is d n, okay, if that is d n is nothing but c of minus n. Okay. So, c naught is equal to a naught by 2, okay, and the coefficients c n and c minus n are given by a n minus I b n by 2, a minus c a n plus I b n by 2, and we can then write c n as the value of c n. Okay. C n can then be written as this 1 over t minus t integral over minus t by 2 to t by 2 f t e raised to the power minus 2 pi n t I by t dt. Okay. So, n takes value 0 plus minus 1 plus minus 2 and so on. Okay. This c n value can be obtained by this a n minus I b n by 2. Okay. We know the value of a n, we know the value of b n. Okay. We put the values of a n and b n to get the expression for c n, and I can combine this, okay, by the fact that this can be written as sigma integral over minus infinity to infinity c n e to the power 2 pi I n t by t. Okay. So, because c minus n, you replace minus n by replace here minus n by some integer n, minus n by n, then n will run for this term from minus infinity to minus 1. So, we can write this series in the abbreviated form like this. Okay. So, we get c n like this, and this is known as c n e to the power sigma n equal to minus infinity to infinity Cn e to the power minus 2 pi I n t I e to the power 2 pi n t I by t as the Fourier complex form of the Fourier series of f, okay, and its coefficients are given by this. Now, the complex form of the Fourier series is useful in problems on electrical circuits having impressed periodic voltage. We can take an example f x equal to e to the power minus x, okay. You are given the interval minus 1 to 1 over which it is defined, okay. We can find the value, okay. You can put here t equal to 2. So, you will get the integral Cn will be 1 over 2 integral over minus 1 to 1 f t e to the power minus 2 pi n t by 2, t is equal to 2, okay, dt, and we can evaluate f t, we know f t is equal to e to the power minus t. We can find the value of Cn and put the value of Cn in this complex form of the Fourier series. We get this Fourier complex Fourier series of the function e to the power minus x, valid in the interval minus x minus 1 less than x less than 1, okay. So, that is all we have to do in this lecture. In the next lecture on Fourier series, we shall consider Fourier integral and Fourier sine cosine transforms. Thank you very much for your attention.